Hello, and welcome to Reducing the Sim-to-Real Gap for Event Cameras. Event cameras are asynchronous visual sensors, where each pixel independently and asynchronously reports positive or negative brightness changes as they occur. The background shows conventional video camera footage that suffers from motion blur. In the foreground, red and blue dots represent positive and negative events from an event camera. Here, images and events are laid out on a timeline. Events are continuous in time, while conventional video is a sequence of discrete image frames sampled at regular time intervals. Computer vision often deals with regular grids. However, events are closer to an unstructured spatiotemporal point cloud. One way to discretize events is a 3D space-time voxel grid. Voxel grid representation is amenable to traditional computer vision tools such as convolution, though sacrifices the continuous time nature and sparsity of events. Our work focuses on reducing the sim-to-real gap, specifically for convolutional neural networks, CNNs, using events. CNNs have become an increasingly popular approach to processing events, yielding large performance gains in image reconstruction, optic flow, and more. CNNs require a lot of training data, ideally labeled with ground truth. Thus, simulation is an appealing alternative to collecting large datasets. A key challenge is training the network to generalize to real data when there is a gap between the appearance of simulated training data and real test data. In this work, we present strategies to reduce the sim-to-real gap, thus improving generalization to real data at test time. We evaluate our method by retraining existing state-of-the-art architectures for video reconstruction and optic flow. To simulate training data, we begin by moving random images along random trajectories inside the simulator. We use the event camera simulator eSIM to generate events. eSIM provides ground truth image frames, events, and optic flow. Here is an example of simulated event data and image frames from eSIM. The key finding is that matching simulator camera parameters to real data yields large improvements for video reconstruction and optic flow. The most important parameter is the sensitivity of the event camera to brightness change, called the contrast threshold. The center plot shows how events are triggered at the level crossings of the observed brightness. Contrast threshold defines the spacing of the level crossings. It is important to cover a large variety of scene motions, lighting, and textures. Modeling camera noise and adding it to the simulated training data also helps. Here we plot the event rate, measured in events per pixel per second for various datasets. The top 5, Cite equals 0.2 to 1.5, are synthetic datasets, generated by tuning the simulated contrast threshold. Each dot represents a short sequence in the dataset. Sequences with a lower contrast threshold tend to have a higher event rate. The bottom two datasets, IJRR and MVSEX, are two popular event camera datasets based on real event camera data. While the contrast threshold parameter of the camera is unknown for these datasets, we can plot the event rate as a proxy measure for the contrast threshold. When we train networks to reconstruct images from events, we find that a network trained on contrast thresholds of around 1 performs best for MVSEC and around 0.2 performs best for IJRR. When we train on the full range of contrast thresholds, we do better yet. This indicates to us that it is possible to get improved generalizability in networks when trained on a wide range of thresholds. The event rate is also affected by scene dynamics and texture. A dataset with faster motions will produce more events than a dataset with slower motions given the same contrast thresholds. Yet, matching the event rate in simulation still works, as long as we cover a large range of scene dynamics and textures. Our retrained networks on the expanded contrast thresholds dataset shows improvements across metrics and across datasets. We report 3 metrics: mean squared error, structural similarity, and learn perceptual image patch similarity for reconstruction. Mean squared error and structural similarity are classical similarity measures, although structural similarity should be preferred, as it is less sensitive to noise and other artifacts than mean squared error. Learn perceptual image patch similarity, LPIPS, is a more modern approach that looks at the distance between the deep features of pre-trained classification networks to measure similarity. We use the AlexNet variant. All of our image reconstruction metrics require reliable ground truth image frames to give a meaningful result. Even though the commonly used Davis line of event cameras do have accompanying frames, many event camera datasets do not have high-quality frames, since the dataset is showcasing some conventionally challenging scenes, such as fast motion or high dynamic range. These images illustrate these issues for IJRR and MVSEC, where events are visible in parts of the scene in which the image structure is completely invisible. As a result, we only post results on carefully curated snippets of these datasets. This motivates our high-quality frames dataset, which has been recorded explicitly to contain the best possible ground truth frames to compare image reconstruction to. Further, some sequences of our dataset contain slow motions or pauses, which have posed challenges to state-of-the-art reconstruction method. Our dataset contains varied indoor and outdoor scenes, in which motion blur and dynamic range issues have been minimized to the greatest extent possible. The sequences were recorded with default settings for contrast thresholds and biases. For optic flow, we use a metric called flow warp loss, FWL, that measures the variance of the motion compensated event image. The cyan lines in the event cloud show the trajectories of events predicted by the optic flow. When events are warped along these trajectories, a motion compensated image of warped events is produced. The variance of that image can be used as a measure of how good the optic flow estimate is. A sharper image will produce a higher variance. Our flow warp loss is given by dividing the variance of the motion compensated image by the variance of the uncompensated image. Thus, flow warp loss is a measure of the improvement from a baseline of predicting zero flow. By training on the L1 loss to ground truth optic flow from the simulator rather than a self-supervised loss, our network is able to predict dense flow. Our results show improvements of up to 40% for video reconstruction and 15% for optic flow. Here are some results on our high-quality frames dataset. On the left, we show image frames from the Davis camera. In the middle, E2Vid is the current state of the art, and we show our results on the right. Here are some results on the color event camera dataset. As in E2Vid, we reconstruct red, green, and blue channels independently, then merge them at the end. For code, datasets and more, please visit our website. Thanks for watching.